So what we're going to do in this chapter is, because we're studying life contingent risks, as I explained in the first hour, what we need to do is we need to be able to quantify the probability of survival or the probability of death of our policy holders. So we need appropriate notation for that. We need an appropriate stochastic model for that. Policyholders' date of death is of course unknown. So this is a random event, something that we do not know, of which we do not know the precise outcome at the moment that we sell the contract to our policyholder. So we call that also in insurance terminology, the policy issuance, at the moment that we issue the policy to our client. So we're dealing here with random events. We need to work with probability. So this makes the course exciting for econometricians and actuarial science students, at least in my opinion. So we need a model for that. We need to be able to deduct probabilities of death, survival at particular ages from this model. So that's what we're going to do in this chapter. And ultimately, if you work throughout this chapter, you should be able to understand, for example, graphics like this one. So this is a graphic that's not in the book. It's a graphic for Belgian data, more specifically for Belgian males. For Belgian males. And what we see here is on the horizontal axis, I put the age. And on the vertical axis, you see the survival function of a newborn evaluated in time point or age X. So basically, and that's exactly what I'm going to explain in the next 45 minutes, what is the probability that a newborn will survive up to at least age X? It's a survival function, so you know from your course on probability theory that that function starts from 1 and decreases to 0. And the idea here is that with these 5 lines, I used data from different decades, even from different centuries, to show you how this survival function for newborn, how this evolved over the years for the Belgian male population. So we see, of course, in blue, for the, let's say, the most recent data, not the most recent, but for a recent decade, you see that the survival function has expanded to the right and becomes more rectangular compared to when you take data from mid-19th century, when life expectancy of individuals was, of course, not as good or not as developed as it is nowadays for people born in the 21st century, right? So we're going to come to that, but that's essentially what we want to try to learn. So where to find these data, how to deal with it in a probabilistic sense, how to visualize these data, and so on. Next to the survival function, you can also look, for example, at the evolution of life expectancy. This is life expectancy at birth, in this case for female data. And you see that I took here a collection of European countries. I've got Belgium, I've got the Netherlands, I've got Luxembourg, Norway, Switzerland, Austria, etc. And I plot the evolution of the life expectancy at birth over the years, right? So again, what do we see? We see a high increase in life expectancy. People tend to live longer. That's the longevity phenomenon, right? And you also see a sort of convergence. You see that the lines here become closer together and they move in a parallel way. So we see a convergence of the life expectancies among these countries that I collected in the graph, right? So this is also something we want to ultimately understand, where to find the data, how to work, how to calculate this life expectancy at birth, how to deal with it. This is for female data. And I think on the next slide, I've got the same graph. I've got the same graph for the males, right? So here you see, if I jump between these two sheets, here you see that nowadays, still, females have a higher expected life, future lifetime compared to their male counterparts for the same age, right? Anyways, so this picture, question for you, from which movie did I capture this screen? The idea is, or the message I want to give here is, of course, I'm teaching a class on life insurance mathematics. I need to assess probabilities of survival, probabilities of dying. I know that this is not a funny topic, of course, but I just want to mention here that this is, of course, a purely mathematical approach that we're going to take, and yeah, it's a not so funny topic, but we need to be able as actuaries to work through the appropriate mathematical tools to deal with this assessments in order to build sustainable pension plans and sustainable life insurance products, of course. Yeah, and then of course I get a lot of feedback from the male students who particularly recognize this picture from The Godfather. So keep this message in mind during the course. I know that some of you may be struggling with personal studies or people in your close family and friends. It's not a funny topic, but we're going to talk here about these probabilities in a purely mathematical way. So let's go. What kind of notation do I need? Well, I need to put together a random variable that captures the future lifetime, or that expresses the future lifetime of an individual. And I'm going to denote this individual with X. So actuaries use the following notation. So X between brackets to indicate a life age, HX, with X being positive. And we're going to look at the future lifetime of a life HX. And of course, that's going to be captured with a positive continuous random variable that I will denote as TX. So the subscript that you have here refers to the current age of the individual. TX is positive because lifetime data are, of course, take positive values. TX is also continuous because I will measure this future lifetime in continuous time. Now, one thing to keep in mind is that if TX is the future lifetime of an individual who is now HX, then X plus TX is going to express the age at death random variable, right? So if TX is 0.5, then X plus 0.5 would be the age at death observed for our specific individual HX. So what we're going to do now is we're going to build up a whole machinery to work with the distribution of TX. And I'm going to start with the CDF. So you will see a lot of concepts coming back that you learned last year in the statistics and probability courses. So in a sense, there is nothing new here. It's just a way of using this machinery now for the random variable TX and its and the human mortality data that are captured to estimate the distribution of this TX. So we're going to denote with Fx the CDF, the cumulative distribution function of TX. So if I take Fx evaluated in T, then that is the probability that Tx is less than or equal to T. So Fx is my lifetime distribution from Hx on. If I look at the survival function, then you know that that is the complement of the CDF. So I'm going to use the notation Sx evaluated in T, and that's the complement of my CDF. So I'm capturing the probability that Tx is beyond T. So these are survival probabilities. These are probabilities of dying before time T. Okay. Now, of course, you can do this for every Hx. So if I do this for every Hx, I've got a collection of random variables denoted here with Tx indexed by X. So what I'm going to do now is make a connection between, let's say, the Tx and the T0, right? Because if you are X-year-old at this moment, then of course, if we go back in time, you were 0 years old at a certain point in time. So what I want to do is connect these random variables together. And this may feel a little bit awkward, but you will see that we can do this in an elegant way using conditional probability. So let us refer to T0 and to Tx. Tx is referring to an individual who is now hx. So x years ago, this individual was 0 years old, right? So if I want to express the probability that this individual will die within t years, then I'm going to look at what is the probability that Tx is less than or equal to t, right? But I can capture that same probability in terms of T0 by saying, well, I want to know what is the probability that the T0 is less than or equal to x plus t, but conditional on the fact that this newborn reached the age of x, right? So if I put that mathematically together, I have the equivalence like this. So the probability that my x-year-old is going to die within t years from now is the same as saying, well, the probability that my 0-year-old is going to die before reaching x plus t, given that my 0-year-old reached age x, right? Because otherwise I could not be saying anything about the future lifetime of this x-year-old. So this is how you can connect these random variables, how you can connect the random variable Tx to the random variable T0 through this conditional expression. So if we manipulate that expression, if I use the expressions for conditional probabilities, then I'll essentially be looking at what you see over here. Yeah? This is something that you learned last year, how to deal with this conditional probability. So let's play a bit around with this expression. So what I'm going to do now is, well, what you see over here is my CDF, the probability Tx less than or equal to t. That's my CDF fx evaluated in t. So I can write this probability, the probability that T0 is between x and x plus t. I can rewrite that as a difference of two probabilities like this. And I can further manipulate this expression because in blue, you recognize the CDF f0 evaluated in x plus t. In magenta, you recognize f0 evaluated in x. And here in red, you recognize the survival function S0 evaluated in x, right? So I'm just playing around a little bit with my notation, with my conditional probabilities. If I then go from this CDF to the corresponding survival function, then I would have to take 1 minus, right? So if I replace this, if I take 1 minus the CDF and I would do the same thing over here, then you can convince yourself that this reduces to the following expression in terms of the survival function. The survival function of an x-year-old evaluated in t is the survival function of my 0-year-old evaluated in x plus t divided by my survival function of the 0-year-old evaluated in x. And I can bring this as 0x to the other side. And then I retrieve an expression that is very useful, which you see here in blue at the bottom of my screen. I also summarize that as a very important expression, summarized on the next sheet. So if we look at S0 evaluated in x plus t, that's the probability that a newborn will reach hx plus t, so will survive beyond hx plus t. And that is then the product of the probability that my newborn survives until hx multiplied with the probability that having survived until hx, that you survive another t years. And we call that in actuarial or in life insurance mathematics, we call this a multiplication rule, right? So this is one of the concepts that you're often going to play around with. So in this case, if you want to survive until hx plus t as a 0-year-old, you first need to survive until hx, and then you need to survive another t years given that you reached hx. And that's what we formally see over here. We can go along and switch from the survival function of a 0-year-old to the survival function of an x-year-old. And what we're now going to do is we're going to derive a similar multiplication rule, but now for an x-year-old. So we're looking here at the survival function Sx evaluated in t plus u. So we want to know what is the probability that our x-year-old is going to reach age x plus t plus u, right? So our x-year-old should survive another t plus u years. What is that probability? So I can express that as follows. It's the probability that my random variable tx is going to go beyond t plus u, right? What I'm now going to do is I'm going to use the connection between tx and t0, which I introduced earlier on. So I'm going to say, well, the probability that tx is larger than t plus u, that's the same as the probability that the corresponding 0-year-old is going to reach age x plus t plus u, given that your 0-year-old is going to reach age x, right? So that's the connection between tx and t0 that we explained earlier on. Using expressions for conditional probabilities, that's the same as what I write over here. So what does that mean? Then I can see this expression as a ratio of two survival functions. The survival function as 0, evaluated in x plus t plus u, divided by the survival function as 0, evaluated in x. If I then further manipulate this expression and I bring in the magenta guys in the numerator and in the denominator, then I can recognize here, once again, a kind of multiplication rule, because I can write the first expression here as the survival probability as x evaluated in t. So the probability that an x-year-old will reach hx plus t, multiplied with the survival probability that an x plus t-year-old will live for another u years. And that's exactly, once again, this multiplication rule, but now expressed for an x-year-old. Yeah. So keep this one in mind as well. This is again a very important expression summarized here on the sheet. If I look at the probability of survival from hx to hx plus t plus u, then that is the product of, first you need to survive until hx plus t. Given that you reached hx plus t, you need to survive another u years, right? So the initial probability that I was asking for, the probability that an x-year-old reaches hx plus t plus u, can be written as a product of two survival probabilities. First, she has to reach hx plus t, and then she has to reach hx plus t plus u. Okay, so these are two multiplication rules that we want to play with, that we keep in mind. And to summarize this once again, I pictured the whole story in LaTeX. So I'm going to start here with my ages at the top of the axis and time at the bottom of my axis, right? So here I look at a 0-year-old at time 0. And I wonder, what is the probability that she reaches hx plus t at time x plus t? So I'm wondering, what is the probability that the blue event will take place? And I can break that up in the magenta event needs to take place and the red event needs to take place. And the corresponding probabilities are expressed here in magenta and in red. If I then do the same thing for my x-year-old at time 0, so do note that I now have different ages versus that I have different age versus time on my x-axis, because now I assume that my policyholder is x-year-old at time 0. And I want to know what is the probability that the blue event will take place. The fact that my x-year-old will reach age x plus t plus u, well, then the magenta event has to take place and the red event has to take place. And again, my multiplication rule pops up for the survival probabilities. Okay, so this is the first thing to keep in mind. Let me just, before taking any questions, bring these properties of the survival function, bring these, or refresh these properties of a survival function. I'm sure you discussed that in another course, but a survival function starts from 1, goes to 0, and must be a non-increasing function, of course, right? So this is important to keep in mind. Here is my picture again. I started from this picture in this second hour of the course. So now I hope this graph already makes a little bit more sense. Huh? So we're looking here at the survival function of a 0-year-old, and we want to evaluate this survival function in points X, where X here denotes ages and time, because I'm looking at an individual from birth on, a newborn individual. And you recognize here the typical shape of the survival function, right? So that was the first point I wanted to elaborate on. Some final mathematical probabilities for this survival function that I will need throughout the rest of the book. We're going to assume here that our survival function is differentiable for all t. We're going to assume that the following limits are 0, which allow us or which enable us later on to calculate the mean and the variance of the random variable tx. So whenever I need these properties, I will come back to them. But essentially, you should keep in mind that, for example, if I want to calculate the life expectancy, then what I want to do mathematically is calculate the expected value of the random variable tx. So at that point, I'll need one of these assumptions to make sure that the mean and the variance, to make sure that the mean exists of my random variable tx. But we're going to come back to those.